dear friend, dear colleagues, it is my great pleasure to welcome you to today's one-word seminar on optimization. So our speaker today is Frank E. Curtis from Lehigh University. I read on his website a very nice story related to his two names, and I enjoyed it very much. So Frank received his PhD from the Northwestern University, and this was followed by 2 years of postdoc at the Curtin Institute of in New York. And after the postdoc, he moved to Lehigh, and he started in 2009. Frank is working on the development and analysis of numerical methods for optimization. He's serving as an editor in the board of the flagship journals in optimization, like Math Programming, MR, SciOpt. So this is all very great. So thank you for accepting our invitation. We are looking forward to your talk. We have 45 minutes.
Okay. All right, thanks very much. Thanks very much for the invitation, the organizers, of course. This has been a great series. And thanks everybody for coming. So today the talk I'm going to give is about SQP methods for constrained stochastic optimization. I'm going to do my best to frame the context here, what kind of problems we're trying to solve and what kind of algorithms we're going to design. This is some joint work with others that are either currently or have been at Lehigh. So first is Albert Barajas, who's postdoc at Lehigh now at the University of Michigan, Daniel Robinson at Lehigh, and Baoyu Zhou, my PhD student at Lehigh. And some work that I'm going to mention at the end is with a new postdoc at Lehigh, Mike O'Neill, on some of the complexity analysis. But for the most part, the work that I'm going to present today is on a paper which is soon going to be appearing in SciAm Journal of Optimization. So I'm going to try to frame the context of the work we're doing here. It's ultimately going to combine things from stochastic gradient methods, people are very much familiar with now these days, and also sequential quadratic programming or optimization, which has been around for a while, solving constrained optimization problems. So that I'll try to give it a little bit of background, or at least the essential pieces that you'll need to know from those different topics as we sort of combine them together in the context that we have here. So a little bit of first the motivation. I mean, I don't really need to say too much about constrained nonlinear optimization. People have been studying this for a few decades now. Whether problems coming from places where you have, say, physical constraints or resource constraints, what kind of objective you're trying to optimize, whether it's costs or minimize energy or whatever it is, these kind of problems have been studied for a long time, and there's plenty of different types of algorithms, penalty methods, SQP, interior point, and so on. Comprehensive theory for these algorithms, even in difficult situations, say when there's a lack of constraint qualifications. I'll talk a little bit more about that kind of thing later. And of course, well-known software that people use all the time. So not to say that there are no interesting challenges in deterministic optimization that remain, but this is sort of the background of the topic we'll talk about today. At the same time, there's also been a lot of work over the years on problems with what I would call stochastic constraints. And I'm just sort of at a high level here explaining that you may have a constraint function that depends on a random variable or comes otherwise from data or so forth. There are different modeling paradigms that people have studied for this context. Stochastic kind of optimization where you're basically looking at expectations, or when you're talking about this kind of formulation, maybe robust optimization or distributionally robust, chance constrained or probabilistically constrained. So this is generally the kind of formulation you would look at when you have some stochasticity in the constraint functions. Okay. What we're going to be talking about today, though, is a slightly different kind of problem where we actually have deterministic constraints. And we assume that the constraints are deterministic, but the objective function is stochastic. Okay, so basically defined as an expectation over some random function. You can imagine classical applications of optimization, deterministic optimization like this, where we, instead of saying we assume that we know coefficients and so forth for the objective, we actually consider it as some kind of expectation. Or maybe even more applications you might consider more modern, or things people are looking at more intensely over the past few years, like training a neural network or something where you actually have constraints, though, that you want to impose on the weight to the network and things like that. So for this particular type of formulation, there are relatively few algorithms so far. There's a couple, or at least an exception that I'll mention soon. And for the most part, they look at things like a penalty method. So throw the constraints up in the objective with a penalty and then apply your favorite stochastic method in that case. But we're going to be interested in actually trying to use constrained optimization algorithms for solving problems of this type. Now, the first thing that we should do is really sort of set our expectations, our goals of what we want from an algorithm in this setting, okay? And in particular, we are going to be interested in what I would call the fully stochastic regime. So what we mean by that is when we look at the objective function in a given iteration, we're going to be choosing a stochastic gradient that may be very noisy. Now you can maybe go and look at sort of adaptive sampling methods that move closer back to the deterministic setting, but we're interested in the possibilities of what you can do in this fully stochastic regime, okay? We also are going to make a few assumptions. So first of all, we're going to assume that feasible methods are not tractable. So in particular, we're interested in problems that might have nonlinear equality constraints, for example. So we're not going to be able to use so easily projection methods. Let's assume that the constraints are not of the form where you can easily project onto them in some kind of manifold, that you can't really do any kinds of projections, for example. And we're not going to be talking here about Frank-Wolf or other kinds of feasible type methods. We're going to be talking about infeasible methods that try to satisfy the constraints sort of throughout the optimization process. And along the same lines, we're not going to be talking also about two-phase methods. We're not going to be talking about a method that's, finds a feasible point and then from there, works towards optimization either in the feasible region or near the feasible region. We're really just looking at methods that sort of maintain feasibility. The thing that is, even in this context, still, kind of a question you might ask is, are you going to force the algorithm to satisfy the constraints sort of deterministically in the limit, or are you only going to ask that you satisfy the constraints in expectation? And the algorithm I'm going to talk about today, we're going to be proving results in expectation. And so, there's still, directions that you might go here to be a little bit more careful with satisfying the constraints, but this is the high level of what we're going to be looking at here, and you can take our work and move on in that direction. Okay. Now, finally, I want to say that we're going to try to set up an approach that is going to be generalizable to other settings. Okay, so let me just mention very quickly an alternative to all of these things. So as an alternative to the fully stochastic regime, you might have a method that uses adaptive sampling, maybe a stochastic line search. And this reference that I give in the footnote in the bottom is a recent paper that came out as an algorithm like that also for our context. So we just have different aims a little bit from what is presented in that paper. So the algorithms are probably not really comparable in a lot of ways. We're looking at things in the fully stochastic regime. Another difference is that we're going to be using a more, a certain type of penalty function that may also be useful when we go to a setting without constraint qualifications and so forth. And that's something that was important to us to set up our future work. Okay. So to make it a little bit simpler, we're going to be focusing only on equality constrained optimization. So think of nonlinear equality constraints with an objective function defined by an expectation. The first thing we're going to do is we need to actually go back to the deterministic setting and set up an algorithm that we could then use to adapt to or extend to the stochastic setting. In particular, many deterministic algorithms for this context would use things like line searches or exact function values to do ratio tests in the trust region method. We're assuming that that's not really going to be tractable for us. So we're going to have to design a different type of algorithm for the deterministic setting. And then we move on to the stochastic setting and talk about our convergence theory. And I can show you some experiments and various open questions and extensions we've been working on. Okay. So first, let me give you a little bit of background in stochastic gradient and sequential quadratic programming. These are things that you're maybe familiar with, but I just want to make sure that I highlight the essential features of those kind of algorithms and their analysis that we're going to need for our purposes. So first, I just like to give a little bit of a plug. So the stochastic gradient method, Robbins and Monroe. So Sutton Monroe is actually a former Lehigh faculty member. I just want to make that little plug for Lehigh there. So here we go. So the stochastic gradient method, I don't think I need to say too much these days. People are pretty familiar with it. You have an objective function, say defined by an expectation or a large finite sum. You assume the gradient is Lipschitz continuous with constant L, and the algorithm is pretty straightforward. You generate a stochastic gradient. By the way, I'm not saying it's the best notation, but our notation going forward is going to be anything with a bar over it is a stochastic gradient that, conditioned that we reached a certain iterate xk, that's the stochastic gradient that we generate, and without the bar is this sort of quantity like coming from the true gradient. So the expectation of the stochastic gradient is a true gradient, and you have some kind of boundedness on the variance of the noise was a common assumption that you would make in this context. So anybody that's talked to me about this knows that I don't call it SGD, I call it SG because it's not a descent method. It's at best you get eventual descent in expectation. And I wanted to put down this inequality here because this is going to be something that I want you to try to remember for later in the talk. So this sort of core theory of stochastic gradient method says, well, the change in the objective that you get in a given iteration, or the expected change, is bounded above by a quantity that is deterministic, okay? So, and I would say an alpha quantity that is deterministic, that is related to an optimality measure of the problem. So in this case, the norm of the gradient squared, plus an alpha squared term that's related to the noise in the stochastic gradient estimates. So without the noise, you would just have the improvement related to the gradient squared. In this case, though, we have that noise, and part of the stochastic gradient method is to balance the improvement from the deterministic part to the noisy part. And you can do that by playing with the alphas and things like that. Okay. So very well known these days, the kind of theory you can get. There's a lot of different types. This is just sort of results in expectation. Things you can say about the stochastic gradient method, that if you have a fixed step size like 1 over L, then in expectation, this is in the non-convex case, sort of averaged gradient is going to be bounded by a constant. And then if you have diminishing step sizes, you can actually prove a kind of lim-inf result for the expected value of the gradient is going to converge to 0. So this comes from a lot of different theory. I don't need to go through the background on this. And we get the kind of classical behavior if you use the stochastic version with fixed step sizes, then you end up bouncing around a neighborhood of the solution like you do on the left, versus diminishing step sizes, you sort of inch closer and closer to a minimizer, hopefully. Now, something that people are probably a little bit less familiar with, unless you've been working in constrained optimization, is SQP. This is a kind of classical approach, but still something that I want to mention a few key things about that we'll need. So suppose now that we have an objective function constraints deterministic, you can really derive in this setting SQP in two ways. One way, you can look at the optimality conditions and apply Newton's method to the optimality conditions. The other is you can set up a quadratic approximation of the optimization problem and look to solve that for your search direction. In either case, you end up with a linear, the step coming from a linear system of the form at the bottom of the page there. That H could be something simple like the identity or the Hessian of the Lagrangian. J is the Jacobian, and you get your search direction D in the primal space, along with your multipliers Y for the dual space. Okay. What the philosophy is of SQP is that we basically trust this direction, and we want to use this direction, and we adjust other parts of the algorithm to accommodate that this is the direction we want to use. And the reason that it's important to stress that is that the direction that you get by solving this sort of SQP subproblem could be one that actually makes the objective function increase. So I'm just illustrating here sort of different scenarios. Imagine that the red is the contour of the model of your objective function, okay? And the blue is your linearization of your constraints. So the subproblem basically says, over the linearization of the constraints, minimize your objective. And what you can actually get is a case like this one on the right, where the objective and constraints are kind of consistent. The direction you get will both move towards the constraints and improve the objective. The one on the left is a little bit different. You can even have situations like this, where a contour of the objective is like that. You're at the point here, whereas the linearization of your constraints is over there. And solving the subproblem actually means you clearly get an ascent direction for your objective. But that's because the constraints are pulling you in that direction. That's what you're going to follow in your constraint setting. So the way that an SQP method, would typically work in some form is that you end up defining a merit function that you're going to use. So your merit function that we're going to use is some parameter that you introduce times your objective function plus a violation measure of your constraints. And this tau merit parameter has to be something that the algorithm is going to adjust. And in particular, in the algorithm framework that we're going to describe, you compute your direction and then you actually adjust tau to accommodate that direction. Say, well, that's the direction I want to use, so I'm actually going to adjust my merit function to make that direction a good direction for that merit function. And then what you can prove is that, in nice situations, that this merit function, eventually this tau will settle down and you'll get actual convergence for the constraint problem towards the optimality conditions, as I'll mention. But just to say that this, in some sense, the optimality measure baked into this merit function becomes a reduction in each iteration of the merit function that you get with your step. So the step produces a reduction in the merit function with this adjusted parameter, and by driving that to 0, you're eventually going to get optimality, as I'll point out. And so a positive reduction in your merit function gives you a descent in your merit function here. So the overall algorithm looks something like this. You have your starting point, and this is a little bit simplified, but just to give you the main idea. In each iteration, you compute your direction from that linear system. That's the direction we want to use. That's what we trust. We adjust the merit parameter to make it so that we have descent in the merit function. And essentially, you're either going to maintain the previous value that you had for that merit function, or you're going to decrease it in order to satisfy, in this case, some inequality of this form. The details of there don't really matter. Just like you're going to maybe decrease it to adjust your weight between the objective and constraints. And then from there, you may do, in this case, I'm just saying like a line search. So this is what I'll call a method SQP backtracking for backtracking line search. So you can do the theory for this pretty straightforward. You under some reasonable common assumptions. The constraint qualification we're going to talk about here for now is the LICQ. So we assume that the constraint Jacobian is full row rank in every iteration. You have a second order sufficiency condition. And then under those nice assumptions, you have nice things that happen in the algorithm. The step sizes are bounded away from 0. The merit parameters eventually settle down at some value that is positive. And by driving the delta Qs, your reduction in the merit functions to 0, you actually get that your steps go to 0, constraint violation goes to 0, and you get primal dual stationarity in the limit. So this is all nice case, sort of classical stuff. What I want to do first is talk about how we can take this algorithm and essentially remove the line search, move more towards an algorithm that will be able to extend to the stochastic setting. This isn't to say that line searches are impossible. In the stochastic setting, you could, and nowadays especially, there's people working on adaptive stochastic line searches and so forth. But we're just going to be looking at the case where we assume that we're not going to do any kind of line search at the moment, right? So we're assuming that line searches are intractable. And instead, what would typically be done is that you would look at step sizes that are related to Lipschitz constants or Lipschitz constant estimates. Okay, so we're going to look at that here. We're going to try to derive such a thing for our context, where we have now this merit function that may be non-smooth. And then we're going to extend that to the stochastic setting. So in the backtracking SQP method, you choose your step size based on reducing the merit function. Here we want to do a similar thing. The challenge is that this is a non-smooth merit function. It's not too bad though. I mean, basically, if you look at the merit change in the merit function from one iteration to the next, and you basically can upper bound it in a similar way using Lipschitz constants for the objective and constraints. It's just that this upper bound is going to be non-smooth itself. But still, just it basically comes, why does the 1/L kind of step size appear in stochastic gradient and other methods, is that you have an upper bound for the function from Lipschitz constants, and you choose a step size to minimize that upper bound, or at least reduce that upper bound. And you can do the same kind of thing here. You just have to account for those different possibilities. There's this kink in this upper bound. And so in different situations, you'll have a step size formula that's slightly similar, but different because of that non-smoothness. So the algorithm that you get looks something like this, and it maybe looks a little bit complicated with the step size choice here, but it's really nothing more than trying to choose a step size that minimizes this upper bound for the merit function. The rest of it is basically the same. You compute your direction, you update your merit parameter, and then you get a step size in this case. And so here we write it in terms of a kind of a loop where you could have certain Lipschitz constant estimates. And if you actually are willing to evaluate the function, you could evaluate the function, see if you get a decrease. If not, you can go back and readjust your Lipschitz estimates and step size based on that. This is, again, sort of still in the deterministic setting where you might use a function values and things like that. But just to point out that we've now moved towards a setting where we could use Lipschitz constants or estimates to compute our step sizes instead of a line search. And what you effectively get is an algorithm that's very much the same as the one with line searches. In terms of proving a lower bound for the step size, in the backtracking line search, it all really depends on how the factor that you use for reducing your step size as during the line search. In this case, when you have Lipschitz estimates, you're basically just adjusting here this row and sort of multiplying their Lipschitz constants until they get sufficiently large. In either case, there's a bound on how small you need to make the step size to get the algorithm to actually behave the way you want it to behave. So the theory for that kind of algorithm is basically ends up being exactly the same as for the backtracking line search. Okay. But now we're going to move to the stochastic setting. And here's where things get a little bit, of course, more complicated. I'm going to present the algorithm in essentially the same form that we just saw. There's just going to be a couple tweaks there that we have to use. And of course, there's maybe further complications in the paper itself, but just to give you the basic idea of how everything works. So here we have our setting again with the stochastic objective and deterministic constraints. We're going to assume that the estimates of the gradients are unbiased and with this bounded variance assumption. Again, I'm going to go back to using bars over quantities. These are basically the ones that during iteration k depend on the stochastic gradient. So certain quantities do not. The Jacobian does not. We're going to assume that the HK matrix we use is also not. You could do that, but that's an extra complication. And so your stochastic gradient affects your direction and the multiplier you get, even though there's also these quantities that are somewhat deterministic in each iteration as well. So here's the algorithm. It looks almost exactly the same as what we would have, what we just presented for the deterministic setting. What we've introduced though, and you shouldn't be too surprised that we do this, is this beta k sequence. So this is going to play a role like you would normally have in the stochastic gradient method of some parameter that you could choose as fixed to get you to a neighborhood of the solution, or you could have it be diminishing to get you actual, like a sort of lim-inf result. That's exactly the role that's being played here. This beta k comes into our step size choice down there. But the overall structure is basically the same as what we just had for this algorithm in the deterministic set. Now, there's one more wrinkle though that we do need to introduce, okay? In particular, so there's this step size sequence beta that, like for stochastic gradient, we could either be fixed or diminishing. But even when we introduce that, there is some additional control on the step size that's needed. If I try to describe it here, but basically you have to keep in mind that we're dealing with a more complicated setting than the regular stochastic gradient method. We have these constraints, and we need to make sure that any potential improvement that stochastic gradient says we might be able to make in the objective, we have to make sure that we're not ruining our progress towards the constraints at the same time. And so we need this little bit of extra control on the step size choice beyond this rule that we came up with here. And unfortunately, we never really know when the step size is too big or too small. It may be too big in the sense that what the stochastic gradient is saying, is progress in the objective may actually move us too far away from the constraints. The step size might actually be too big, on the flip side, too small, the step size, because you can compute a stochastic gradient that maybe is 0, even though you haven't optimized. That's fine in the regular stochastic gradient setting. You just keep going, and maybe in the next iteration, compute another gradient that will move you farther away. But in any case, there's this extra factor. We don't really know what exactly is going on because we're balancing these two things, feasibility and optimality. And so what we ended up doing is introducing this interval. So we basically compute the step size as we described, and then we project it onto an interval. And this interval has a very particular width to it related to beta squared for reasons that you might expect, that we have to make sure that the interval is not too wide if we're making diminishing step sizes and we actually want to force convergence. So there's plenty more to investigate in that, but I don't think we want to go too much into the weeds there. With those choices, we end up being able to prove a result that looks like this. And this is where I want you to remember back to the stochastic gradient setting, where the change in that, the sort of expected change you saw in the function was like a deterministic quantity related to an optimality measure. In that case, it was like, minus alpha, the gradient, true gradient squared, plus things related to noise. And that's kind of what we get here. We get a deterministic upper bound part that's related to what the true step would be if we had the true gradient. Then there's another term related to the noise, okay? This is related to the noise in the gradient. And then there's actually a third one that only comes in because we're doing, we have a constrained setting, this one here. And essentially this comes in as well because of the adaptiveness of our step size related to the merit function, and also the tau parameter that's changing as well. So these are some additional, again, complications beyond the regular stochastic unconstrained setting. So this extra term pops up. And this is another reason why we have to have more control on that step size choice. But in any case, so with that, there are other lemmas that we would need. We need to sort of bound inner products of the stochastic gradient and the stochastic direction. We're able to do that. The direction itself ends up being unbiased in terms of what the direction you would get in terms of the true gradient, but otherwise we need these various bounds on inner products. And ultimately, the careful choice of that projection interval allows us to bound that last noise term, again with something that we can control with respect to our beta sequence here. And we can prove, very much mimicking what we see in the stochastic gradient setting, that if we have a fixed beta, at least for, once the merit parameter settles down, we have a fixed beta, then we can prove that the expected average delta Q, and remember, delta Q is basically related to the optimality measure of the constrained problem. So the sort of long run average delta Q is going to be bounded by a constant if we had a fixed step size, sort of a neighborhood of a solution. And otherwise, with diminishing step sizes, we can get a result like this. And we can, actually put this in terms of our optimality conditions to get a result of this form. It's basically one step from there to turn those delta Qs into something related to primal dual stationarity and constraint violation. So again, we are not necessarily proving that we deterministically, get to feasibility and optimality, but we do get this convergence and expectation with relatively loose assumptions just on the stochastic gradients so far. Now, one more caveat though that I do need to say is that this result requires an assumption about the behavior of the merit parameter and the merit parameter sequence. This is something that the algorithm is adjusting adaptively based on stochastic quantities. And so, you could imagine that there are scenarios, realizations where things could get out of control. Now, there are some bright side to this, though. Essentially, what you really want the algorithm to do is start with, whatever starting merit parameter you use, you want it to eventually adjust down to a level that is small enough, but not vanish. So it's sort of below a threshold. And this is the result we get in that setting. The other possibilities that you worry about is that because of the stochasticity of the gradients, the merit parameter might vanish. But we will say that this would not occur if you actually had some more boundedness on the stochastic gradient estimates. So if they were uniformly bounded, that would be, everything would be fine. This wouldn't happen. I also say here, and this is in red because this is more of a conjecture, that if you had, say, variance that diminished more quickly, then you might be able to prove things like with high probability, at least over some finite number of iterations, the tau would not get too small and things like that. This is a little bit getting into the weeds, but this is something that we need to consider for our setting, that, with bad gradients, this kind of thing could potentially happen, although only in sort of situations where the gradient estimates become really extreme. The other possibility is that the merit parameter would actually not get small enough, so that you're not actually driving, you're not reducing enough of the weight of the objective, and you might actually not get towards feasibility like you need. But this would only occur, and I can say more about this offline, but if you have realizations of the gradients or stochastic gradients that are in some sense one-sided consistently over many iterations, that you end up getting unfortunate, like biased in one way, your stochastic gradients. So this is, if you have a symmetric kind of distribution of your stochastic gradients in general, this is going to happen with probability 0, but it's still something that is possible. So we have done a little bit of experiments on this, and just as a relatively straightforward one, we just took some problems from this well-known Qt collection of test problems. All we did here, not too sophisticated, just added noise to the gradient estimates. We ran our algorithm for about 1,000 iterations, and then we ran a stochastic subgradient method on a merit function. And for that one, we actually, just to give it as much chance as possible, we used the merit function with a whole range of merit parameters. We ran each instance with more iterations many times, and we just collect here sort of the best iterate that each algorithm was able to produce over that whole run. And comparing the best iterates you get from stochastic SQP versus stochastic subgradient, we have the figures here. So for different levels of noise, for very little noise, we're able to get very accurate in terms of, we at least get a feasible iterate, and pretty good in terms of optimality over here. These are just regular box plots. As we inject more noise, we see that we're still generally able to get feasible with our algorithm, although optimality is not necessarily as good as we get with little noise, but overall uniformly better than the stochastic subgradient method. Let me just very briefly mention a couple of extensions. So all that work that I just mentioned there is in a paper that's going to appear soon. We have a few other projects that we're working on that basically extending or moving in different directions in this space here. So one thing we've been working on is a complexity bound for this kind of algorithm. We don't necessarily expect here to get a result that is better than what you might see for a stochastic subgradient kind of algorithm applied to a merit function. But what we find is, what the challenge here is again, we have an algorithm that has an adaptive merit parameter update. And because of the sort of potential failure of the algorithm to either to set that decrease that parameter too much or not enough, and because of the stochasticity, we don't know when it's doing it the right thing it's supposed to do. This is actually quite a challenging thing to come up with, but we're pretty certain we're getting there, and we have a conjecture at this point that will hopefully be completed soon in terms of our proofs. But the conjecture generally is that if you ran the algorithm for some k iterations with a fixed step size, and the merit parameter ends up being reduced S max number of times, which is generally speaking going to be much less than K max, you would expect that if you were to choose this is a common in sort of complexity analysis of non-convex settings, where you say, well, then if I randomly choose with the, in this case, a uniform distribution over all the iterates that I've run, and look at the delta Q, which is again like an optimality measure for that at that iterate, I expect it to be something like constant over square root of K max, the number of iterations that I've run. Okay, this is consistent. If we had, if I showed you the details, this is consistent with the kind of thing you would see for stochastic gradient, subgradient in non-convex settings. But again, our extra challenge here is that merit parameter. We've also extended our algorithm to the setting of relaxing constraint qualifications. So in this case, if you don't have the LICQ, you could actually have infeasible or degenerate problems. And we switch in that case to an algorithm that uses a step decomposition method, basically a step decomposition towards one step towards the constraints, one in the null space towards optimality. And these look like this exact same kind of plots that I had before, but they're basically for a new algorithm. And the problems that these were run with all have degenerate constraints. So the Jacobians all have singularity in them. And you can see that the algorithm basically behaves the same way as before in a similar comparison to stochastic subgradient. One or two other quick things that we're also working on. Another paper that hopefully will be out relatively soon is on a matrix-free version. So one question, one immediate question you might have from what I presented before is that, okay, if these are large scale problems and you have that big linear system to solve every iteration, maybe I can't even conceive of doing that. It's just too much work, in order to handle that. Well, what we've been working on is what if you apply a iterative solver in a sort of matrix-free way toward those linear systems and terminate the solves early to get an inexact direction. So this is combining stochastic gradients and inexact subproblem solves. And we have an algorithm that should be able to handle this case and essentially give the same convergence guarantees as the first algorithm that I presented. Naturally, you end up with a few user-defined parameters you got to control when you're balancing stochasticity and inexactness, but we present the algorithm in a way that gives you a lot of flexibility for different applications to kind of tune the algorithms for those settings. And finally, of course, there's the case of inequality constraints. We've looked a little bit about SQP in this context, although large-scale inequality constraints with SQP in some cases are often beat out by interior point methods. So we've also started to look a little bit at stochastic interior point methods as well. All of these are challenging because, again, in the constrained setting, you have these extra parameters that your algorithm is adapting to make sure that you satisfy feasibility and optimality, and all of those things become more complicated in the stochastic setting. So just to wrap up, I guess I maybe finished a little bit early, but hopefully there are some questions we'll see. We have presented an algorithm for equality constrained stochastic optimization. This required a little bit of a step back to the deterministic setting to set up an algorithm that would more easily extend to the fully stochastic setting. So we then presented a stochastic SQP method, talked about convergence and expectation. I think there's a lot of ways to go from here for people that are looking for, extending it beyond ways that we've even done, different types of convergence guarantees and so forth, different related settings. The numerical experiments that we showed at least are certainly outperforming what might be the natural thing that people try who don't work in constraint optimization, just applying, use a penalty or something like that. We believe our methods have a lot of advantages over that kind of thing, especially once we introduce our extra, enhancements about inexact subproblem solves and so forth. And other extensions as well, different complexity bounds and inequality constraints and so on and so forth. So with that, I think I will end and take any questions if you have any. Thanks very much.
Thank you very much for a nice talk. Very nice results. Are there any questions, remarks?
I would have a question. Hey,
Matthias.
thanks a lot for the talk. I would have a couple of questions actually. I was quite interested in that. So in the beginning, you said something about the step sizes, the alpha K, which I found a bit irritating. So you said in the beginning, the alpha K is deterministic throughout your methods, but that can't be really true, right? Because you choose it adaptively sometimes. And then of course it depends on some problem data, which are random by nature.
Right, no, of course. Maybe if I said that, I might have misspoke, or maybe there's something that was wrote. So basically, yeah, the alphas adapt with the merit parameter. The betas basically play the role of the what you would normally think of the predetermined sequence. Yeah.
Right. And did you maybe also do a comparison with your adaptive strategy for the alpha K and an amigo kind of strategy? Did you see some? Are they comparing in the same way, or?
In the deterministic setting, we did just as a sanity check, and as you would expect, there were results for the, as I would expect anyway, that the Armijo rule in a deterministic setting is still a little bit better.
Yeah.
Our adaptive approach was sort of a little bit worse, just because you have to adapt those Lipschitz estimates, but it's at least competitive that it's enough that you can then move to the stochastic setting. Yeah.
All right. Okay. Interesting. And if you allow me, Radu, I would have a second question as well. If it counts as the second question, not as the third. So the construction you have here, you're essentially reducing the merit function, if I got you right? In the construction of the algorithm. Yeah. So there are, of course, classically interior point kind of methods where instead of a merit function, you look at a potential function, which usually has some kind of barrier term as the complicating part, which by construction then gives you feasibility though. So that's the main advantage.
Right.
So why would you advocate now your merit function approach instead of the potential function minimization approach? Because for the equality constraint case, theoretically, you have a nice barrier set up, so you can directly go with the potential reduction mechanism as well.
Sure. I mean, I think there's, I think all of these types of methodologies should be explored. The one thing I do worry about, and even in our exploration of, say, interior point methods and things like that, is the way that interior point methods generally would work is you have a barrier parameter that you fix, and then you optimize to some accuracy, and then you continue. But now you have a setting where you don't know when you've optimized to any accuracy because everything is based on stochastic gradients. And so your decision of when to decrease the barrier parameter now becomes something that is uncertain. And the way that people would, sometimes address that is you run some prescribed number of iterations and decrease it. But this is, so those should be explored as well. Mm-hmm. But, one thing that I at least like for the equality constraint setting in this context is you don't have to, pick a parameter, optimize, and then change it and then optimize. You don't have to have that now uncertainty. You just run it from the beginning like this. But each one should be explored, I think. Yeah.
I see. Okay, thanks a lot. Interesting.
Sure. Thank you, Matthias.
Yeah, so I'd be curious to know how would your method compare to, say, something like vanilla stochastic gradient in the absence of any constraints? Would you be much better through the adaptivity, let's say, of your step size, or?
Oh, I guess in terms of the adaptivity, I mean, I guess people have looked at that. I haven't, adapting your Lipschitz constant estimate based on, say, stochastic function values. We haven't explored that for this setting because we've been focusing on the constraints, but I imagine there are settings where that would also be preferable to the fixed Lipschitz estimates and things like that. Yeah.
Okay, thanks.
Sure.
Thank you. Jonathan?
Yeah, so I was just wondering, so in your tests, you were just adding some mean zero noise to the Q?
So yeah, so for the ones that I presented here, because the other ones we're doing are, not finished yet, so I didn't want to present them yet. But we've been looking at things like constrained, logistic regression or other regression, optimal control problems with stochastic objectives. So we've been running some experiments like that. They didn't seem finished or enough to the point where I wanted to present them today, but we've been doing other ones as well.
Because I think what would be interesting is a kind of machine learning, type of thing where you're trying to minimize the average of a whole bunch of functions, and you just pick a batch or a mini batch. And this would probably give you, it's bounded noise, but it's much more violent noise than what you're trying. It'll be interesting to see how the algorithms work in that setting.
Absolutely. And for any of my students who are listening, I think that's, yes, you could tell there's going to be interest in testing those things. So yeah, definitely.
Thank you. Matthias?
Sorry, yes. So Jonathan's question now provoked me actually asking another question. So what would happen if you have randomness also in the constraint? Can you handle that situation as well?
So, what you would do then probably is you have to decide what would be your modeling methodology in that case. Is it going to be, what do you want in terms of the constraint? Do you want it to be satisfied an expectation with high probability, yes, almost surely, and then that would probably influence what kind of algorithm, if our algorithm would even be able to be used in that setting. So it's a good question, but I think this setting, even without both in the objective and the constraints, there's maybe a need for the algorithms in this case. So that's what we're looking at so far. But that, of course, those kinds of problems would be interesting too. Yeah. There's certainly a lot of what I've seen in some papers recently that would be related to your question is people want to impose constraints. Like say you have a machine learning problem where your objective function is a large sum or kind of like an expectation, but you want to impose constraints on certain samples or certain subset of the data set. Mm-hmm. And there, though, you have a lot of potentially constraints that you probably are not all you want to enforce deterministically, but with, also consider them as sign of stochastic. I think that there's definitely opening for algorithms in that setting too.
A simple example would be, because you mentioned PD constraint optimization. So suppose you have a random PD constraint optimization problem, and then you have some obstacle on your solution trajectories, right? Mm-hmm. That would be a natural case where you have a random constraint as well. And then naturally the question arises, how do you formulate actually the situation in an appropriate way? Okay, but you haven't looked at that case so far.
No, not yet, no.
Great, thanks.
Sure.
So we have a question on the result on the last slide. So John is asking, so if you can go to the last slide.
The one with this one, I guess.
This is the very last slide. So John is asking, what flavor is the sandwich?
What's the flavor of the sandwich? Oh, it doesn't matter, but I knew I was going to want one after this, so yeah. Okay. Probably with lettuce, tomato, maybe BLT. That sounds pretty good right now.
Okay, so then I propose to stop here.
Oh, I have a question.
Oh, we have more questions.
Mark,
yeah.
Yes.
Sorry.
Can you go back maybe to the linear equation systems you had there with the 8 sub k, the Hessian? I don't recall you're actually saying where you got your Hessian estimate or 8 sub k from, and what you're doing with that.
Sure. So, and as I was saying, one possibility is just you have that as the identity. So it's sort of like a first order method in the constraints. We've been playing around experimentally with having it be more like Hessian of the Lagrangian, although in that case, you also need to worry about stochasticity in your multiplier estimates. So something that maybe at least tries to incorporate some maybe stochastic second order information about your objective and your Hessians of your constraints, which are deterministic, although coming up with what are the good multipliers to use there is another open question in all of this. So maybe I don't have a satisfying answer yet, but we're experimenting with the things that you might consider trying, either simple HK or more like moving towards the Hessian of the Lagrangian kind of thing. We're experimenting with those different variants now.
So the results you showed were all based on using the identity matrix, which essentially amounts to steepest descent or gradient, not necessarily descent, as you were saying?
Yeah, so in the experiments that we showed, we do that. Although, yeah, with more recent experiments that I haven't included in the talk, we're doing more moving away from that. Exactly.
I guess I'm not really used to when you're using the identity, you're calling that sequential quadratic programming. I mean, technically it is, but I'm used to the
Oh yeah, sure it is. And just like if you had a quasi-Newton matrix there, you'd still call it SQP. But it's true. Like basically what we're doing is we're, in some sense, computing a direction that is gradient projected onto the linearization of the constraints. But you know, in general, we're just setting things up to move away from just H equal the identity. I mean, all of the algorithms that you have for stochastic gradient and variants like, you know, SVRG and Atom and other kind of things where your second order matrix is some, you know, diagonal scaling or other things, you could incorporate those as here as well.
Because when you have a quasi-Newton, then of course you'll get errors propagating from the gradients into the quasi-Newton Hessian estimate. You could use potentially, if you have a way of directly stimulating or estimating for the Hessian, you could do that, but now there needs to be a noise term on the Hessian. And then actually when you're going and trying to do your simulated performance with your experiments, you have to worry about what the actual true relation between the noise and the Hessian and the noise and the gradient would be to make it realistic.
Exactly, and that's the challenge people have with Newton, quasi-Newton in the stochastic setting in general. And so basically, in order to do a large-scale test, we do things like the identity, but in general, problem dependent, you could introduce more things.
So thank you very much.
Sure.
Then let us stop here. So let us thank Frank E. again for the very nice talk, and we had a very nice discussion and many questions. So it will be just in the spirit of our seminar to move from a stochastic SQP method to a talk on optimal transportation and application to learning. This will be next week, given by Gabriel Perez. So the slides and the video of the talk today will be online. So thank you very much. Have a nice week. See you next Monday.
Thank you again, Radu. Thanks.
Thank you.